Hi everyone, welcome to another ACE session. We are in Unit 5, carboxylic acids, and therefore it's appropriate to talk about their acidity, their acid-base properties. The problem that I want to do right now is complete the acid-base reactions below, label the acid and base, show the mechanism, draw the products, label the conjugates, and the last part, draw the appropriate equilibrium arrow, and we can use the pKa table to help us do that. Our first pairing is shown here. Let us decide which one's the acid and which one's the base. You don't really need a pKa table to do that because you should know that carboxylic acids have a pKa around 5. Now if you have a fluorine here, it may be lower. If it's closer, it may be even lower. But in general, you should memorize that carboxylic acids have a pKa of around 5. Now we have an anion as its partner. Anions are more basic because they want to grab a proton to become neutral. Typically, charged molecules are less stable, so we don't need a pKa table to understand that this is most likely the base and this is the acid. Let me get you started, and then I'll probably ask you to do the first 4, A, B, C, and D, and then we'll talk about the equilibrium together. How I want to get started is if I know or I have a good guess at what the acid is, make sure you draw the bond to the proton that you want to remove. Now, one may ask, well, what about all of these hydrogens here? And heck, what about this hydrogen here? How come this molecule can't lose this proton? Well, hydrogens that are connected to carbons are not very acidic. And let me show you the pKa table that I provide my students. And when I say that a hydrogen connected to a carbon is not very acidic, I'm thinking about these hydrogens. See, the pKa is very large, 60, 45. Here was a little bit lower, 26. That's the terminal alkyne. We didn't need a pKa table to understand that none of these hydrogens are more acidic than this one on the oxygen. Let's get back to our drawing. We want to draw this bond for sure, and then I'm going to draw the base so it is facing the proton that I am going to remove. Now, a phrase that I have my students memorize is the base lone pair grabs the proton, or you could say the lone pair of the base grabs the proton of the acid. Either way, it helps you remember that the arrow goes in this direction, the mechanism arrow. Hydrogen cannot have more than one bond. It looks like we're making a bond between sulfur and hydrogen. Therefore, you have to break that bond, and that's fine. Oxygen is electronegative, so it can accommodate that negative charge that you're going to make at that oxygen. Okay. I'm going to ask you to pause the video and fill in the products and label. Label the acid base, conjugate acid, and conjugate base. Okay, we're going to save the equilibrium arrow for last. That's part E. But our product looks like this. And now we have to determine, label. You can remember that the acid, when it loses its proton, becomes the conjugate base. And when the base grabs a proton, it becomes the conjugate acid. I remind my students that a conjugate acid is an acid. Look what happens when I go backwards. To go from the products back to the starting material, who is losing their proton? It's this sulfur that's losing the proton. So this is acting as the acid going in the reverse direction. So the first phrase again that I talked about was the lone pair of the base grabs a proton of the acid. A second phrase is equilibrium favors the weaker acid. So you have to choose which compounds you want to compare. You want to compare the two acids, one on each side. Do we know which one is the weaker acid? I don't. I know that this is a pK of 5. I could write that right now, actually. But the thiol is a pK that most students do not memorize. the thiol. That's the full pKa table that I provide my students on the exam. And honestly, we have a sulfur here, but that's sulfuric acid. We have a sulfur right here. See, that represents any alkyl group. This is the closest thing. Equilibrium favors the weaker acid. The higher the number, the weaker the acid. And we saw that when I talked about hydrogens connected to the carbon. Not very acidic. Negative. Large negative numbers, very acidic. The weaker acid is this methane thiol, and we're going to draw our equilibrium towards the weaker acid. So I am explaining with pKa values that we are going towards the weaker acid, the one on the right, but it also makes sense to think of it this way. Between these two acids, which one is more likely to lose its proton? Well, since this is the stronger acid, it's more likely to lose its proton, and the direction is to the right. So you could even think of it as the equilibrium favors the stronger acid losing its proton. It's up to you how you want to memorize the phrases that talk about the equilibrium arrow. Okay, for the next pairing, we have a carboxylic acid. Right away, I'm going to use a pKa of 5. And here we have an amine. Do you notice how I am classifying each molecule? That helps a lot in classifying or figuring out its properties. So we have an amine, and this is a carboxylic acid. I'll just abbreviate it. pKa of 5. What about this amine? Well, you got to be careful, because on the pKa table there are certain or several molecules that have nitrogen. But we would never pick up a pKa for an N+ if our molecule potential acid is neutral. We need a neutral nitrogen, and we could also say that that nitrogen has 3 single bonds. That may be important for some pKa tables, but here our neutral nitrogens are just here. There's one there, 36. Every other nitrogen I see is protonated and positive. Positive. Pyridinium, positive. Aniline, positive. We're going to use 36. I'm not looking up the pKa's to determine the equilibrium arrow just yet. I'm using the pKa's to tell me which one's the acid and which one's the base. For some problems, you will be looking at the pKa table twice. Once at the beginning to figure out which one's the acid and which one's the base, and once at the end to figure out the equilibrium arrow. Does it favor the right or the left? Let me get you started with this, but remember, now we have proof. This is the more acidic molecule, it has a pKa of 5, and from the pKa table, that amine is 36. R group NH2, good. R group NH2. It's a good match. A lot of times you're not going to have as good of a match. You just have to pick the best from the pKa's that are available. Let me start you off. I'm not going to draw the mechanism arrow, but I want us to start off by drawing the Lewis structure, not the condensed. And make sure you have the bond that's connected to the hydrogen that you're going to lose. So I wanted to start it off this way because here I use a condensed structure, but when you draw the mechanism, you got to see the bonds, and you might as well draw the rest of it so you can see how this is a carboxyl group. The amine, I'm going to flip because I want the nitrogen a little bit closer to the acidic proton. One way you could write that is H2NCH3. Okay. So the only hint I've given you is, for this problem, is draw the bond to the hydrogen. I didn't give you any lone pairs. You got to remember which one's the base, which one's the acid. So I'm going to pause the video, or you'll pause the video, and you'll draw the products. Well, you should draw the mechanism. arrows first, draw the mechanism arrows first, draw the products, label the acid base and the conjugates, and then when I come back, we'll talk about the equilibrium arrow. Or you could try it on your own if you have that pKa table. Okay, phrase number 1. Lone pair of the base grabs the proton of the acid. I don't have any lone pairs. I don't see any lone pairs, but I do know that nitrogen with 3 bonds has 1 lone pair. That is the basic site. Grab the proton. Make sure hydrogen gets ejected or donated. So here's a trick, or here's something tricky. Remember initially, I wanted to look at the pKa to see which one is the acid. So I did look up the pKa's. The pKa of this equals 5, as usual. Here the pKa equals 36. And at that point, I knew that this was the acid of the pair. So I'll put here acid. This is the base. This is the conjugate base. And this is the conjugate acid. The base becomes the conjugate acid. This is where some students trip up, because now they remember equilibrium favors a weaker acid. Well, you're not looking at this pKa anymore, because in this reaction, this molecule is not even acting like the acid. So this pKa is now irrelevant. You want to pick the 2 acids, one on each side, and find their pKa's. So we're not looking at the pKa for this, we're looking for the pKa of that. You can see how this is going to be very dangerous, because if you look up the pKa of this, you'll get the wrong answer. Because, yeah, we do have several entries where there's a nitrogen, but we're looking for the one that's protonated. Therefore, a common mistake is picking up 36 as a pKa of that. Very similar, except that this one is protonated and has a plus charge. Where is that best or better match? The better match is up here. Protonated amines have a pKa of 11. There's one exception. Ammonia, which is a protonated amine as well, is a little bit lower, pKa of 9. But we have R groups. So this is a protonated amine, pKa 11. pKa equals 11. And again, it is helpful to be able to classify these molecules. Okay, weaker acid, weaker than that. We ignore this because this is not even the acid anymore, it's a base. Weaker acid, we're going to the right. Very interesting. We make a pair of ions, one negative and one positive. You may think that that's unusual because you may have heard that nature hates charges. Well, that phrase was mainly helping us work with resonance. Why is it stabilizing to spread out the charge? Here, just go with the acidity. We know that this is a weaker acid. You're going to make it because this is a stronger acid. The last example is this carboxylic acid again. By the way, this is called benzoic acid. We have HCl. What's the difference between these two examples? Is that HCl is a very strong acid. It has a pKa of -4. So when you have hydrochloric acid with a plain carboxylic acid, this is now acting as an acid. They're right next to each other. Between these two pairings, this would be the acid. Therefore, this has to be the base. So that's strange that the carboxylic acid now is acting like the base, because now this is the stronger acid. It will be the acid reactant. We're going to draw out the carboxylic acid again, showing the carboxyl group Lewis structure. Now, the thing is, I've been drawing the bond between the O and the H in the first two cases, but I know that this is not the acid. So I'm not going to strip off any hydrogens here. I'm actually going to strip off a hydrogen off of HCl. And see, I made a mistake. I should draw the bond, because that's the bond I'm going to break. Okay. Now, the question is, when you think about the lone pair of the base grabs the proton of the acid, that's the acid now. Well, which lone pair? They're both sets are on oxygen. Which one is more basic? We went over this concept in a previous video where we looked at a situation where the carboxylic acid is the base. Let me find that screenshot real quick. It was this video where we saw that the carboxylic acid at the bottom is actually acting as the base. And in that video, we went over which oxygen is the basic site, which oxygen is going to do the grabbing. From our analysis, and you could go back and watch the video, from our analysis, the proton that was, the oxygen that grabbed the proton was the top oxygen. See the product all the way on the right? That's when the top oxygen is protonated. That happened to be the most preferred site of basicity. And we'll see that again in this problem. Do you remember what that last video concluded? It was this oxygen that's more basic. If you don't know why, rewatch that video. And then our products are this. That actually has resonance, but I'm not worried about resonance in this video. We did have an anion as the conjugate base, right? Let's label. This is now the base. This is the acid we have to look up the pKa for, and it's a very unusual acid, right? It's the protonated carboxyl group. If you recall, this has a pKa of, in my chart, it's -4. Yeah, just a reminder, these pKa values can vary pretty quite a bit from pK table to pK table. My table, it's -4, but I have one from the textbook, and I believe HCl is here. Whoa. So that's a little bit different. It's -7. It just depends on the experimental conditions by which they measure the pKa. But either way, I'm pretty sure that's going to be a stronger acid than this one right here. So, man, maybe I should double check that, because this is a pretty strong acid as well. I want to make sure that I draw the equilibrium error towards the weaker acid. Let me find one more pK table, the definitive source of pKa's in my mind. I googled Evans pKa table, David Evans, and here's the pK table that is the go-to if you couldn't find a value that you needed in other tables. Now, let us pick up, we're going to go with this table. Let's say HCl is -8. Okay. So I'm going to change that on our sheet in just a bit. But where is that protonated carboxylic acid? Ooh, I didn't realize it was so close. Here we have -7.8. -7.8 for this protonated carboxyl group. If I'm going to use this pKa here, I should be using the same source for the HCl. -8, -7.8. Let me revise this, and I'm going to put here -8. And for this conjugate acid, I'm going to say pKa equals -7.8. Very interesting. Depending on the pKa table, it may actually switch. But in this case, that's the weaker acid by barely a little bit. But I'm going to follow my rules. Equilibrium favors the weaker acid.